When using context-free grammars, for instance for parsing, it is often helpful to first transform these grammars into a nice form. And one such nice form is the Chomsky normal form. First, we will see that we can transform a context-free grammar in such a way that it no longer contains rules that produce lambda. A production rule whose right-hand side is lambda, the empty word, is called a lambda production rule. A variable a is called erasable if the variable a can be rewritten to the empty word lambda in one or more steps. The set of erasable variables can be determined as follows. First of all, if we have a lambda production rule, then the left-hand side is an erasable variable. Moreover, if we have a rule a can be written to b1 up to bn, so the right-hand side only consists of variables, and if all of these variables in the right are erasable, then also the left-hand side a is erasable. Which is clear because if we can erase all of them, then we can rewrite the right-hand side to lambda, meaning that a is erasable. And these two are sufficient to determine all of the erasable variables. Let's have a look at an example. Here we have a context-free grammar and we want to determine the erasable variables. First of all, b is of course erasable because we have a lambda production rule with left-hand side b. Now, since c can be rewritten to bb and both variables in the right are erasable, also c is erasable. Now we know that c and b are erasable and a can be rewritten to cbc. All of the variables in the right are erasable, meaning that a is erasable. Now our variable s is not erasable because there is a terminal symbol in the right. So the set of erasable variables is the set containing a, b, c. For every context-free language L, there exists a context-free grammar G without lambda production rules, such that G generates the language L except for the empty word. And this latter restriction is needed because if we have a grammar without lambda production rules, then we cannot derive the empty word. So let's start with an arbitrary context-free grammar and let's transform it into a grammar without lambda production rules. How do we do this? As a first step, we are going to determine all the erasable variables of our context-free grammar. So all the variables that can be rewritten to lambda. Next, we are going to add fresh rules, and these fresh rules will make sure that the lambda production rules are no longer needed. So whenever we have a rule of the form a can be rewritten to x, b, y, where x and y are arbitrary words over terminals and variables, and b is an erasable variable, then we are going to add a fresh rule a can be rewritten to xy. So what's the intention of this fresh rule? The idea is that our variable b is erasable, and if we remove all the lambda production rules, then b will no longer be erasable. So this fresh rule caters for this case that we would like to erase b, but we no longer have lambda production rules, so the b is already pre-erased, so to say. And we are going to repeat this for all the fresh rules that we add. So also for these fresh rules, we are going to check whether the right-hand side contains erasable variables, so we may need to add more fresh rules derived from this rule. Once we have added all fresh rules possible, so nothing more can be added, then the lambda production rules are no longer necessary and we can throw away all the lambda productions. The resulting grammar generates the same language as our original grammar, except for the empty word. Now let's have a look at an example. This is the context-free grammar that we would like to transform into one without lambda production rules. As a first step, we determine the erasable variables. Clearly B is erasable, C is erasable, and since B and C are erasable, also A is erasable because it rewrites to BC and all symbols in the right are erasable. So the set of erasable variables of this grammar is ABC. S is not erasable, contains a terminal symbol, and likewise D is also not erasable. Now we transform this grammar into one without lambda production rules. We start from the original grammar. So this is our original grammar, no changes have been made yet. We are now going to add fresh rules, and these fresh rules are obtained by dropping erasable variables from the right hand side of rules. So let's start with our rule S can be rewritten to ABAC. A is erasable, B is erasable, and C is erasable. So let's start by dropping A. If we drop A, we get BAC. If we drop B, we get AAC. If we drop C, we get ABA. Now we have three fresh rules, and we have to again check whether there are erasable variables that can be dropped from these fresh rules. And indeed, in this fresh right hand side, we can still drop B, and we get AC. We can also drop C, and we get BA. Now, from this fresh rule, we can drop A, we get AC, which we already have. We can drop C, which gives us AA. From this fresh right hand side, we can drop A, which gives us BA, we have that already. We can drop B, which gives us AA, which we also have already. So now we have to check this fresh right hand side. Here we can still drop the C, so we get just the lowercase terminal letter A. Here we can drop B, which also gives us terminal A. Here we can drop capital A, which also gives us terminal A. Okay, so we are ready with adding fresh rules for S. Let's look at A. A can be written to BC. Again, both B and C are erasable. So if we drop B, we just get C. If we drop C, we get just B. Now from C, we can still drop C, which gives us lambda. Also from B, if we drop B, we get lambda. From our rules B, there's no variable to be dropped. From C, we have one rule where we can drop the D, but we already have the lambda. And from this rule, nothing can be dropped. So we have added all the fresh rules that we need. Now the final step is we are allowed to drop all the lambda productions. That means we are allowed to drop this, and this lambda rule. And this is our final grammar. This grammar generates the same language as our original grammar, except for the empty word. And our resulting grammar no longer contains lambda productions. Next, we will see how unit production rules can be removed from context-free grammars. A unit production rule is a rewrite rule A can be written to B, where both A and B are single variables. For every context-free language L, there exists a context-free grammar G that neither contains lambda nor unit production rules, and that generates the language L except for the empty word. So we are going to show that every context-free grammar can be transformed into one without lambda and unit productions, and it produces the same language except for the empty word. We have already seen how we can transform a context-free grammar such that it no longer contains lambda production rules. So let's assume that we've already done this step, so we start from a grammar G that does not contain lambda production rules, that produces the language L except for the empty word. And now we are going to remove the unit production rules. As a first step, we are going to determine all pairs of variables a, b, such that a and b are not the same variable, and a can be rewritten to b in one or more steps. So we have a derivation from a to b. In determining these variables that have these derivations, it really helps that we have already removed the lambda production rules. Because if we have a grammar without lambda production rules, then if we are deriving, words can never get shorter. We cannot rewrite something to lambda. And since words cannot get shorter, in these derivations we do not need to consider words that are longer than a single letter. So to sum up, in order to determine all pairs of variables a, b, for which there is a derivation from a to b, it suffices to consider the unit production rules. We do not need to consider any other rule of the grammar. So this makes it very easy to determine these pairs of variables. Now, once we have determined these pairs of variables, we add fresh rules as follows. Whenever we have a pair of variables a, b, such that a has a derivation to b, and there is a rewrite rule b can be rewritten to y, then we add a fresh rule that allows a to be rewritten to y. The intention of this fresh rule is obvious. If a has a derivation to b and b can be rewritten to y, then also a has a derivation to y. This fresh rule allows to do this derivation in a single step, bypassing all the unit production rules that we have used in this first step. Now, once we have added all fresh rules derivable in this form, we are allowed to drop the unit production rules. And the resulting grammar will generate the same language except for the empty word. And actually the empty word we have lost already in the first step of the transformation, namely when we have removed the lambda production rules. Let's have a look at an example. We take this context-free grammar and we're going to transform it into one without lambda and unit productions. The first step has already been done. There are no lambda productions in this grammar. So next we are going to determine all pairs of variables a, b, such that a has a derivation to b. In this example grammar, we have a derivation from s to b. We also have a derivation from a to b, and from b to a. Now, since there is a derivation from s to b and from b to a, we also have a derivation from s to a. And since there's a derivation from a to b and from b to a, we also in principle have a derivation from a to a, but we are only interested in those derivations where the start and the end of the derivation are different from each other. So we are not going to add the derivations from a to a and from b to b. Okay, so these are the pairs of distinct variables that can be derived from each other. Next, we are going to take our original grammar and we are going to add fresh rules. Let's start with s. We have a derivation from s to a, and we have rules for a. So now, since we have a derivation from s to a, we add as possible right-hand sides for s all right-hand sides of a. So from a we can get terminal a. We can also get BC, and we can get B, but we already have B as a rule for S. Now, from S, we can derive B. So we also have to add the right-hand sides of rules for B as possible right-hand sides for S. So from B, we can get capital A, and we can get BB. So we add also capital A and BB as right-hand sides for S. Now let's have a look at the variable a. We have a derivation from a to b. what are the right-hand sides of B? We have A and we have BB. For B, we have a derivation from B to A. So we have to add the right-hand sides of A. We get terminal A, we get BC, and we get B. So these are all the fresh rules that we can add. And now, since we have added all fresh rules, the unit productions are no longer needed, and we can drop all the unit productions from this grammar. So if we drop all the unit productions from this grammar, this is the result that we get. So from S, we have dropped B, since this is unit production, and A, since that's unit production. From the rules for A, we have dropped B and A, and from the rules for B, we have dropped A and B. And the remaining rules are not lambda productions and not unit productions, and they give rise to the same language as the original grammar, possibly except for the empty word. In this case, the original grammar does not produce the empty word, so they actually give rise to the same language as the original grammar. We've now seen how we can remove lambda and unit production rules from context-free grammars, and we are going to utilize this for transforming context-free grammars into Chomsky normal form. A grammar is in Chomsky normal form if all of the production rules have one of these forms. So every Chomsky normal form is a context-free grammar. The left-hand side of each of the rules is a single variable. But not every context-free grammar is in Chomsky normal form. The Chomsky normal form additionally requires that the right-hand side of each rule consists either of two variables or a single terminal. So in particular, observe that the Chomsky normal form enforces that there are no lambda production rules and there are no unit production rules. The right-hand side is never lambda and the right-hand side is never a single variable. We will see that every context-free grammar can be transformed into Chomsky normal form. So that means for every context-free language L, there exists a grammar G in Chomsky normal form, such that the grammar generates the language L except for possibly the empty word. And again, we cannot expect the empty word to be generated because Chomsky normal forms do not contain lambda productions, so it's impossible to derive the empty word from the starting variable. Every context-free grammar can be transformed into a grammar in Chomsky normal form. The first step of this transformation is the removal of lambda and unit productions. And we've already seen how this can be done, so we assume that this has already been applied, so we are starting from a grammar that contains neither lambda and unit productions. And it generates our language L except for the empty word. Next, we're going to continue to bring this grammar into Chomsky normal form. The first step is that for every terminal letter A, we add a fresh variable CA together with a rule that allows CA to be rewritten to A. So for every terminal letter, we have a fresh variable that can be rewritten to this terminal letter. Next, we are going to transform our rewrite rules. We are going to transform those rewrite rules where the right-hand side has length 2 or more. So if we have a rewrite rule A can be written to x1 up to xn, where n is 2 or more, and our letters x1 up to xn can either be variables or terminals, then we are going to apply sigma to each letter in the right-hand side. And what does sigma do? Sigma of x is just x if x is a variable. So sigma leaves variables unchanged. And if x is a terminal, then x is replaced by cx. So in short, if we have a rule whose right-hand side is length 2 or more, then we are going to replace all the terminal letters in the right-hand side by the corresponding fresh variables that we've just introduced. And once we've done this with all the rules, we have to do one more step, namely we have to split rules in order to make them shorter. If you recall, then in a Chomsky normal form, the right-hand side consists at most of 2 letters. So if we have rules where the right-hand side consists of 3 or more variables, then we have to shorten the right-hand side. And the idea is simply that we split each of these rules in 2 rules. And we've seen this idea already applied when we've transformed right linear grammars into strictly right linear grammars. Also then we have split the rules. So how does this work? If you have a rule, A can be rewritten to B1 up to Bn, where n is greater or equal to 3, then we are going to split this into 2 rules. We're introducing a fresh variable c, and we replace the original rule by 2 rules, one saying that A can be rewritten to B1 up to Bn minus 1c, and c can be rewritten to Bn minus 1 Bn. If you apply both of these rules after another, then we basically get our original rule, but now the right-hand sides are shorter than the original rule. So we keep splitting until all of the rules have at most length 2 in the right-hand side. And once this is done, our grammar is in Chomsky normal form. Let's have a look at an example. We're going to transform this grammar into Chomsky normal form. First, observe that the lambda and the unit production rules have already been removed from the grammar. So we can immediately continue with the next step. The first step is to introduce fresh variables for the terminal letters. So we have terminal letters A and B. We're going to introduce fresh variables CA, CB with rules CA can be rewritten to A and CB can be rewritten to B. Next, we are going to transform all those rules of our grammar where the right-hand side has at least length 2. What are we going to do? We are going to replace the terminal letters in those rules by the fresh variables that we've just introduced. So we start with this right-hand side of our rule for S. We replace A by CA and B by CB. We replace all the terminals in the right-hand side because this right-hand side has length at least 2. So we get CAS CBX. This right-hand side is fine because it has length only 1. Here we have a right-hand side of length 2, so also here we should replace the terminal letter by the fresh variable, in this case CA. Here we have another right-hand side of length 3, so also here we should replace the terminal letters by our fresh variables, so we get CA, CB, CA. Now we are almost done. The only thing remaining is to split those rules that have more than 2 letters in the right-hand side. So we have 2 of these rules, this rule for S and this rule for X. We're going to split this rule, and I'm going to do 2 splitting steps at once. So we get 2 fresh rules and 2 fresh variables. We have fresh variables S2 and S3. So now S rewrites to CA S2. So we produce the CA. From the S2 we get S and then S3, and the S3 produces the CBX. If we take this together, so if we assume that we apply this rule followed by the rule for S2 followed by the rule for S3, what do we get? Then we get S rewrites to CA S CBX. And that's exactly our original rule that we've split. There's one more rule that we need to split, namely this rule. So we introduce a fresh variable x2, and we say that x2 rewrites to CBCA. So now our resulting grammar is in Chomsky normal form. If we look at each of the rules, then the left-hand side is just a variable, so we have a context-free grammar. And if we look at the right-hand side, then we see that each right-hand side either consists of precisely two variables or precisely a single terminal. We have two variables, single terminal, two variables, single terminal, two variables, two variables, two variables. So we indeed have a grammar in Chomsky normal form, and it generates the same language as our original grammar, except for the empty word, but the original grammar did not produce the empty word, so it produces exactly the same language.